Hello and welcome back to my next video where yesterday I've been going through Andrej Karpathy's lectures, Neural Networks 0 to Hero, well, the first one, where he remakes his own framework for neural networks called Micrograd. Who Andrej Karpathy is? Basically, he's one of the founding members of OpenAI. He worked at Tesla, back to OpenAI, and now he's doing his own AI education company venture thing. He's one of the leading AI researchers, I guess, is what I'm trying to say, but if you're here, you probably know him if you're in the space. I will let him introduce himself as well.
Hello, my name is Andrej, and I've been training deep neural networks for a bit more than a decade. And in this lecture, I'd like to show you what neural network training looks like under the hood.
So basically, in his lecture, he goes through what the neural network is. He's an amazing educator. I've had so much fun listening to him and like learning from him. So basically, the idea is that he's gonna go through what a neuron is. In a human body, neuron basically processes and transforms information into some kind of output, right? And the same can be said about neural networks, meaning we have some inputs. Inputs are basically data. Data have some weight. Then inside, let's say in the blob of things, there are some mathematical expressions and certain bias selection, randomness, this sort of thing that combined produces an output, and the output is the result of the mathematical expressions. So the idea is that he has on GitHub, he has a Micrograd, his own small library for neural nets. This is basically, he was remaking things and explaining things as he went with some errors, debugging and so on, which was very helpful to the learning process, right? Basically, we are defining here some mathematical operations that are necessary for the neural net to work. Then some backwards propagation. I will explain that later in a moment. Yeah, this is the whole backpropagation. And then we used, or he used actually, I just followed graphics for visualizing things. He created some examples before he went to actually create a neural net. Let me go down to that. Yeah. Basically, if you don't want to remake what he did, which is the tiny grad, PyTorch has everything already created, right? He just wanted to show us the most basic things, or most basic operations that are needed, right? We don't need a whole PyTorch library. We can just write it out ourselves. Yeah, so he defines neuron, which is basically a number of inputs. They have weight and bias. A layer of neurons, and the multi-layer perceptron is basically like defining how many layers how many number of layers we have. The idea is when learning, or we're actually training a neural net, we have some input data. We have the neural network. This is our input data. Basically, we're working on tensors, and in the tiny grad, he was working on scalars, just to show how this works. But basically, in production, in real world, it'll be tensors, right? So arrays of of values. When teaching a neural net, we have the input, and then basically we know how we want the output to look like, right? So we know the desired targets. In this case, 1, -1, or -1, 1. The idea is now that if we, when teaching neural net, right, there is something called the forward pass. So basically, when we input, when we give the data along with the weights to our neural net, after the mathematical expressions define what the output is. Once we have the output, we can calculate the loss function. Loss function meaning how well our neural net did. Basically, the lower the better. There are multiple ways how to calculate the loss function. And here he used something, well, he used mean squared error, but on production, he mentioned that there is, usually it's binary cross entropy, so a different type of loss function. Once we know how well our neural net did, we can do backpass, mean backpropagation, basically calculating the gradient for each operation or for each like moment in the neural net. Based on that, based on the gradient, we can do gradient descent, basically update the parameters, the gradient parameters. The gradient parameters define how those certain moments in the neural net, the mathematical expressions at any point in the neural net, how they impact the output. So we can adjust those to make it more or less impact the final output, right? And then however many iterations we do, we should get closer. If we are going in the right way, we should get closer to our desired targets, right? So the idea is that if we do 20 passes, then from 0 to 19 we should start going closer to 0 in this sense. This will show the loss of data. So let me just reinitialize the neural net, and then this is the 20 passes, right? So we start with the loss at 6.45, 3 and 0.035, 16 and so on towards 0. So the more we do this, the more we go towards 0, because we are training our neural net to get better and better at predicting what we want. And this is how it looks like. This is kind of funny. When I saw this first time, I was kind of amazed, because it doesn't look complicated when you actually go through with Andrej. When you go through all the operations and stuff, you write them yourself. It doesn't seem that complicated, but then it quickly grows in complexity once you actually start like visualizing things and like adding things. So yeah, let me summarize the lecture, and then I will actually let him do the same because he's a much better educator than I am. So what I took from this at a high level, what are neural nets? Math expressions that take input data and weight params of neural nets. Math for forward pass. Basically the idea is, yeah, as you see, even on this graph, there are certain mathematical expressions that we do in order to calculate, and at the end we have our output, right? Loss function, we try to measure accuracy of a prediction, low when predictions are matching the targets, behaving well. We want the loss function, or we want the neural net to have the lowest possible loss function. So we manipulate the gradient in order to do that. We need to calculate the gradient with backpropagation to see how or what impacts the neural net how. Then we tune all the params to decrease the loss locally. Basically here, this is this step by minus 0.1, at least in this case. This is a very like fine-tuning, it takes practice. And then we iterate many times in gradient descent, follow the gradient to minimize loss. We did 20 passes each time this loop ran, right? And yeah, that's kind of it. It took me 5.5 hours, I think. 5.5, dear God. 5.5 hours, but I had trouble setting up the Jupyter lab on Mac, because I installed Python with Homebrew and it hit the fan, and I had to like debug for like an hour and a half. But if you're watching this and you have the same problem, or you want to set this up on Mac, I recommend just doing Miniconda, and that's very, very easy. It took me like 5 minutes to set it up with Miniconda instead of like debugging. I should have went there, but I was pretty stubborn. Yeah, I'll let Andrej also summarize this himself in case, well, I probably wasn't that, will not be as clear as him. So let's hear him.
So let's now bring everything together and summarize what we learned. What are neural nets? Neural nets are these mathematical expressions, fairly simple mathematical expressions in the case of multilayer perceptron, that take input as the data, and they take input the weights and the parameters of the neural net, mathematical expression for the forward pass, followed by a loss function, and the loss function tries to measure the accuracy of the predictions. And usually the loss will be low when your predictions are matching your targets, or where the network is basically behaving well. So we manipulate the loss function so that when the loss is low, the network is doing what you want it to do on your problem. And then we backward the loss, use backpropagation to get the gradient, and then we know how to tune all the parameters to decrease the loss locally. But then we have to iterate that process many times in what's called the gradient descent. So we simply follow the gradient information, and that minimizes the loss, and the loss is arranged so that when the loss is minimized, the network is doing what you want it to do. And yeah, so we just have a blob of neural stuff, and we can make it do arbitrary things. And that's what gives neural nets their power. This is a very tiny network with 41 parameters, but you can build significantly more complicated neural nets with billions, at this point, almost trillions of parameters. And it's a massive blob of neural tissue, simulated neural tissue, roughly speaking. And you can make it do extremely complex problems. And these neural nets then have all kinds of very fascinating emergent properties in when you try to make them do significantly hard problems. As in the case of GPT, for example, we have massive amounts of text from the internet, and we're trying to get a neural net to take like a few words and try to predict the next word in a sequence. That's the learning problem. And it turns out that when you train this on all of internet, the neural net actually has like really remarkable emergent properties, but that neural net would have hundreds of billions of parameters.
Yeah, as you can probably see that he's very well-spoken, and I can highly recommend this lecture and probably the next ones. Yeah, I can't really believe that this is like free information on the internet. This is from 2 years ago. Yeah, August 2020. So I guess I am at a starting line of 2020, and I'll try to catch up to what are the best practices and knowledge in 2025, or up to 2024, I guess. Since we just started. Thanks for watching, and see you in the next one. Bye.